Well, thanks for having me. This has really been a fantastic session. So this talk is going to be, as you'll see, a bit more applied than the previous talks. But one thing I just want to say up front is that there are lots of interesting theoretical questions that I will sort of allude to as we're going through. And if anyone is interested in this, I would love to talk about this. So feel free to ping me afterwards. So, okay, so the work I'm going to tell you about was done by a group of people. It sort of started with Yohai, who was then a postdoc at Harvard. And then there's been a group at Google, especially Stefan, Dima, and Jamie, who sort of implemented what I'm going to show you in the second half of this talk, which is sort of algorithms for solving turbulent flows. And I just wanted to make sure I acknowledge that up front. So, okay, so this has grown into a huge field, and the previous sets of talks have been just a fantastic introduction to all of the great work that's going on. And I think in the spirit of the previous speakers, I'm not going to be scholarly in this, but I'm going to try to just explain what we've been doing and try to give some insight into why we've been thinking about things this way in the hopes of stimulating discussion. And so we all know that PDEs pervade the physical sciences. That's why we're all here. And what we always tell our students is that PDEs represent an infinite number of degrees of freedom. But we also all know that that's not true. And historically, I guess I would argue that the major goal of applied mathematics has been to find ways, however, to reduce the number of degrees of freedom for specific situations. And essentially every approximation method that we've ever invented is to this end. Including numerical methods, of course, which work by solving large flow problems or large PDEs on grids. And this has already been discussed by the previous speaker, but this is just extraordinarily expensive. And not only is this expensive, it really doesn't scale very well. So, for example, the movie on the left, which is a movie of a hurricane in 2017 that was done by NASA, the cost scales at least like 1/4 the mesh spacing to the fourth power. And, there's never, as we all know very well, there's never enough computing power. And so I mean, how do we solve equations? This is all review, but I'm just trying to express the framework that we're thinking about it. So of course, the numerical methods that we've always used to solve PDEs are quite old. What we have always done is to take the equations, to discretize them, and then to derive a discrete numerical update rule based on calculus. And this numerical update rule, there are various schemes, for example, in turbulent flows for modifying the update rules by averaging or doing whatever. But at the end of the day, one has a numerical update rule. And the sort of crux of the matter is that even for relatively simple simulations, we can't actually afford to do a direct simulation of even the Navier-Stokes equations, which is like the simplest complicated equation that I could imagine. And this is canonical, but let me just remind you all why. I mean, if you just consider the Kolmogorov cascade and you use it to compute the number of Kolmogorov eddies that are in a box of size L, then sort of simple arithmetic shows that scales like the Reynolds number to the 9/4 power. And if you then say that every small eddy needs 1,000 grid points to resolve it, I mean, that's an overestimate because maybe you don't need 10 points per dimension, but you need some number of points per dimension or some number of basis functions. Then you end up with sort of this formula for the total number of grid points. And if you start plugging in numbers for even simple things, you end up with, insolvable problems for which the solutions can't be stored. And I mean, I think that this is really striking to remind ourselves of this frequently because, this wasn't possible when we were all children. It won't be possible when we're all old, and it won't be possible when our children are old. This is like, kind of an unsolvable, tragic situation that we have these beautiful equations and we just don't know how to solve them in detail. And I mean, this is, sort of practical, a picture of this is that this is a sort of the sort of grid spacing. So this is, a hurricane off of the east coast of the US, and this is the resolution and the state of the art global circulation model. And so, there's a lot of stuff happening in each of these little boxes. And of course, the fact that this has been averaged over has caused us to incur errors in the solutions, but that's basically the most that we can afford. So with that in mind, what I'm going to talk about today is essentially a set of ideas we've been developing about how to modify the numerical update rule of the PDEs to make it so that it is more efficient at solving, the equations as they are. So we are, the philosophy of this, which I think is sort of an interesting contrast with several of the previous talks is that our goal is to use as little machine learning as possible, but to use enough so that we can improve the efficiency of the numerical solver. And I believe that at the end of the day, there's going to be a continuum of methods that that one could imagine, addressing, and those methods will have different advantages and disadvantages that we can discuss at the end of this talk. And we're trying to hit a sweet spot where we're trying to minimize the amount of machine learning, but putting enough in so that it's helpful. So, okay, so I'm gonna, so we've been working on this for a couple of years, and I actually don't have time to get through all of this, but what I'm gonna do today is focus on sort of two things. The first is a paper that we published 2 years ago, and I'm giving the references just in case you're interested in this and I go too quickly or I'm unclear. The first is, the method is we call learned discretizations, and I'm going to just first explain it via 1D examples, and this was sort of in this proof of concept paper. And then what I'm going to do is show you talk about a paper that we just published a couple of months ago, which applies this to 2D turbulence, which is where it starts to become interesting, and we can talk about performance and scaling. So the ideas that underlie what I'm going to tell you about were sort of first originated. I was having an interesting conversation with Payman Milanfar, who's now at Google, who has for years worked on super resolution for images, and he invented a very interesting algorithm which he calls Razor, which basically works on the super resolution problem. So it takes an image and it downsamples it, and then of course what you try to do is to recover it at high resolution by using, for example, some interpolation, and or you could use in modern world neural networks. And what Payman showed was that actually a efficient way of doing this was to train a bank of linear filters. So there's no, and then what you do is on every little part of the image, you look at it, you measure some statistics or whatever of the image. Sort of eigenvalues, think eigenvalues of Laplacian or something like that. And then you use those to choose the particular averaging operator that you're going to apply to that piece. And then you use that to upscale. And that was interesting because, each of these sort of averaging kernels is kind of like, it's an interpolation function, right? It's exactly what we need for numerical analysis. And when Payman was explaining this to me, I was like, well, we should do this for PDEs because that's a much easier problem than doing it on all consumer images. I mean, doing it on all images is a hard problem, but like even, as bad as the solutions to the Navier-Stokes equations or whatever your favorite equations are, the solution manifold is finite dimensional for sure. And so this sort of same thing has been done with neural networks. And our goal was to basically, figure out a way to apply this way of thinking to PDEs. And I would point out that the sort of bicubic interpolation case is roughly, I say every standard numerical method, I guess that's dangerous in this audience, but many standard numerical methods are basically in this category. And the question is, can we do better? And can we do this in such a way that we can do time evolution? So I'm going to first illustrate this in a simple 1D setting, and then we will progressively be more complicated. So imagine that I give you a bunch of curves, which are initial conditions for the solution of some PDE. So how do we proceed? So what we do, of course, is we choose grid points. We then erase the curves. And then our job is, if we want an update rule for the PDE, we need to be able to estimate spatial derivatives, the relevant spatial derivatives of the solution at each of the node points. And of course, if all you're given are these points, which have been deliberately chosen to be undersampled, then if you do something like fit them to polynomials, we all know the trouble that we get ourselves into. And this sort of ends up being gives unstable numerical methods. And it's the reason that, if you have a shock like this one, you need to use higher resolution than this if you'd like the method to converge. So on the other hand, if I tell you, so this is the thought exercise, suppose that I tell you, as you presumably guessed, that these are actually solutions to Berger's equation, and I moreover tell you that I can generate an entire library of curves which are solutions to Berger's equation, now you can build a regressor to basically compute derivatives based on these solutions as examples. And of course, if you do that, you'll do much better because you're no longer considering general functions, you're only considering functions which are on the stable manifold of the equation of motion. And so, this is kind of obvious. It's kind of a simple point, but our goal was to invent numerical methods which basically follow this philosophy. And what we're going to do is use machine learning. When I said we're only going to use it in small little bits, we're going to use it to do interpolation. basically. That's the goal, is to use it to do the sorts of interpolation that I just said. Now, in order to explain what the results that I'm going to show you, I just want to make sure that it's clear what the question is. So the question is, suppose you're given a high resolution simulation. You can, of course, simulate this using a standard method at high resolution, and it costs whatever it costs. So you could also compute what one might call an exact coarse graining of the solution. So I'm going to take the solution and I'm going to represent it on a coarser mesh by simply taking the solution and averaging it over little boxes, the size of boxes that you see in this. And this represents the exact coarse graining of the high resolution simulation. So what our goal is, so actually there are two separate problems. So one is, given this movie of the exact coarse graining, how could you reconstruct the original high resolution simulation? I will claim this is straightforwardly solvable, and I will neglect it for the rest of this talk. Instead, what we're going to talk about is, suppose that you're only given initial data on the coarse grid. Can you invent an update rule that integrates it only on the coarse grid, which therefore will be less expensive because it's on a coarse grid than on the high resolution solver? So that's the problem that I'm going to talk about. So I'm going to show you, as we go through this talk, lots of comparisons between, I'm going to show you lots of comparisons, of accuracy of things. And I want to emphasize that the accuracy is relative to time rollouts of coarse-grained solutions. Okay, and of course, we all know that in standard numerical analysis, this is what we teach our students. If you simulate on a grid that's too coarse, which is precisely what we want to do, you either get something which is unstable, or you get something which is inaccurate, like the numerical diffusion causes it to just go away. And the question is to somehow avoid this. Okay, so fundamentally, what we're going to talk about is replacing rules like this one with machine learned alternatives. So that's the basic idea. And actually, I should say, as we get a little further, I will generalize this slightly to slightly different ideas, but conceptually, this is the concept. So I'm just going to plunge forth, but if anyone has any questions, then ask. As I guess we've all learned now, it's kind of disconcerting to talk to your computer if no one says anything. So please. So okay. So here's here's the idea. Here's an example of how neural networks are put in. So imagine I give you a solution on a grid. And so this represents the interpolation operator, the standard interpolation operator, right? Like I can think of the U's as being, as being, fit with some basis, and I then can differentiate the basis. And these alphas give me the coefficients for computing the derivative in that basis. So what we're going to do instead is we're going to imagine that I give you U's, in some, some range around the point in question, the point xn, where I want to know the derivative. I'm then going to send the U's through a neural network, and I'm going to predict these coefficients from the neural network. And I will train this in a way that I'm about to show you, but I will train it essentially to allow for accurate time stepping. So the method is, and this has been touched on before in Sid's talk, in several of the talks before. Like I've touched on this as an idea of a method. So what we're going to do is perform many high resolution simulations, but only of small pieces, because we don't aspire to learn the global solution. We just want to learn the little local interpolation rules, and then we will train the regression algorithm and see how well it does. So this is the full neural network for the 1D problems that I'm going to show you. Sorry, I've tilted it, so this is probably not good pedagogy. So here's the values of the function at the grid, on the grid points, which we're going to push through a neural network. The last layer of our neural network, what we do is we project the coefficients that we're computing onto polynomial accuracy constraints. Because of course, if you demand that the second derivative is second order accurate, then that corresponds to a relationship between the coefficients, and you can just project onto that subspace at the end, which essentially allows you to demand that the method will recover classical, well, at least demand, that will suggest that the method will recover, classical interpolation when nothing interesting is happening and the resolution is sufficient. So we then compute spatial derivatives, but then to train it, what we do is not quite what I alluded to, which is we compute the fluxes using these derivatives. We then compute the time derivatives. And then what we do is we create a loss, which actually turns out it needs to be a multi-step loss for numerical stability. There are lots of bugaboos in this. One is ensuring that algorithms like this have long-term numerical stability. And what we found is we need multi-step, we need to do multi-steps, from these formulas. And then we essentially use these to train the weights of the neural network to allow the rollout. We do this on some training set, and then we then if you want to run the model, you just run it this way. So that's basically how this works. And just as an example to sort of get you in the mood for what this looks like. So this is the stencils that are learned from doing this on Berger's equation. So these are the stencils for the first derivative. So this is a shock. This is a shock. The dashed line is the high resolution solution. The solid line is the level of resolution that we're doing. And the way that we compute derivatives, that the stencil for the first derivative operator varies as you go throughout the domain. So for example, at the shock, the stencil is quite different than it is when the solution is smooth. And this is the point, basically, is to somehow learn things like this, which of course will only work for equations with these features, but that's the game that we're playing. And I mean, so hopefully this movie will play. I mean, basically, I'm going to show lots of quantitative evidence about this in the Navier-Stokes equation. And so I'm not going to belabor it really much in this, but this, even out of the box works very well. I mean, baseline with 64 points diverges, the neural network, I mean, you see the orange things or tracking the things works quite well. And the way that we evaluate accuracy, at least in this initial paper, the way we evaluated accuracy, how you evaluate accuracy is a very important subject in this business. But in this is that we did the following. We trained in a domain which went from 0 to 2 pi. So this is space and this is time. So we trained in a domain that was this big, but then we tested in a domain that was 10 times bigger and for much longer times. And this is an example of a simulation which is upscaled by a factor of 32 from the baseline. And when we plot the mean absolute error, and this mean absolute error is computed over basically this part of the figure. So it goes up to time 15, and it's the whole domain, which is 10 times bigger than the training domain. So when we compute mean absolute error as a function of resample factor, then let's see, these are different methods. This is first order, third order. This is the Wino method, the red dots. This is the neural network. And actually the green dots are sort of amusing. I mean, one of the fun things about automatic differentiation is you can demand that it gives you whatever you want. And so we simply asked, can you please find us, constant coefficient stencils so that it has a chance of with flux limiters, so that it has a chance of competing with Wino. And it essentially reproduced, right, the accuracy of the Wino curve, which is amusing. And anyway, in this initial paper, we tested this idea in the models learn upwinding. There's an interesting question about what the models learn. I'm going to skip this. So in this initial paper, we tested it on a bunch of 1D PEs, as you're supposed to do. And, it basically worked. And that's that. Now, of course, this is all just a toy because there's no reason. I mean, we don't need 1D PDs. We don't need numerical solvers for 1D PDs. Okay, so just one other comment. If any of you are interested in this, as I said at the beginning, I do think that there are lots of interesting mathematical questions here, which I would love to talk to people about. But another thing we did, this was a Harvard student, Xiaowei Zhuang, who is also an intern at Google, who actually did this for the advection equation, which is really trivial. It's nice because it's really trivial. And this is, this is sort of compares first order methods versus so, we start out with a square. So you should just see the square advect, and the neural network sort of beats the baseline. But what's nice is, and I think I have this, is that Xiaowei has a GitHub link with his code in it. There's a Jupyter notebook for just doing this for a 1D advection equation, which I think, as a theoretical problem is the place that I would start. So I just wanted to flag this. And then I'm going to move on to what I see as the most relevant, is we're going to talk about turbulence. So does anybody have any questions? Yeah.
Yeah. Sorry, maybe I don't know if that's the best place to ask
please stop me.
So you were insisting about the locality aspect of your kind of learning cells. So is this locality, infused into your choice of architecture, or is there any place more explicit? Maybe I missed.
It is infused. So our architecture is like, you choose your stencil size. Just think standard numerical analysis. Like you choose your stencil size at 5 points, right? Your architecture then takes in the value of the function at those 5 points, and you spit out whatever number of interpolation coefficients you want, which depends on the order. And then, it's just some stack, we optimize whatever, but that's it. So it's purely local and it's translational. So that operator works everywhere.
But it's more like acting as a kind of bilateral filter, in the sense that the coefficients of the filter depend themselves on the value of the function.
Yeah, that's right. That's exactly right. I mean, so like I said, this was inspired by Payman's thing that I showed you at the beginning with the thing. And I mean, so it's literally just a local operator. So as I said, just to remind you what I said at the beginning. The hope here, and I mean, was to put in as little machine learning as possible and see how well we can do. And in fact, if anyone could think of a way of putting in less, I would be very interested, right? Clearly, we can put in a lot, but this was the attempt to be minimal. Other questions? Okay, so now I'm going to talk about turbulence. Actually, we've been, there's a question in the chat. I don't know. Can you repost the link? Yeah, I'll post the link. Sorry, but let me talk now, because if I post the link, I will stop talking and the whole thing will go down. Okay. Our goal is to learn a discrete update rule, and I already said this. Our goal is to learn the discrete update rule such that the coarse grid solution matches the fine grid, and we have to reduce computational cost. So this is only interesting if it reduces cost. If it doesn't reduce cost, it's a complete waste of time because we already have algorithms. So I just want to be clear on this. And I also want to say that if this works, and I am going to argue that this works and works quite well, it works as well as it works, and it doesn't work any better. Maybe that's a better way to say it, that it works, that this is, I think, a different type of solver than those usually expressed in computational fluid dynamics. And the reason is that traditionally in CFD, the way that we've gotten around the fact that we can't resolve anything is, of course, to change the equation. Namely, what you do is you take the ordinary spatial update rule, you add a correction to it, which, for example, large eddy simulation, in which you have parameterizations of the turbulent viscosity, of course, grained over the grid point, and then you use that to basically solve. And this is the workhorse, right, of much of science and engineering. But typically, the metrics for evaluating LES codes are statistical. So, for example, here is a classic paper from Tom Hughes' group from 20 years ago, in which they show that the LES methods, match spectra, which is great. You, of course, want it to match spectra. We'll talk more about this, but really, what we're trying to do here is to match time evolution, right? Like point-wise time evolution, as I said before. So how do you choose an update rule? So I'm now going to take a step out, basically. I'm going to walk out, which I think, John, this gets a little bit to your question. Everything I'm going to be talking about is local. So we're always going to have update rules that depend on the local environment of the grid point that we're trying to update. And you can choose how local, but for the purposes of this talk anyway, we could talk about spectral, but I'm not talking about spectral. I'm just talking about local things. But even within the world of local things, you can choose G. There are lots of choices. So for example, you could choose G to be a neural network. There's no reason that you need to start. I mean, you could just use your favorite ResNet thingy, whatever, to stick this in and get a pure update and to get a neural network update rule. So that's one choice. So a second choice that you could do, and this is what I just explained to you, is that you could do what we call learned discretizations, in which one essentially uses the neural network to pre-process the velocity field to compute these interpolation coefficients, and then use the equations of motion to get the update. So this is this way. But then there's one more. This picture motivates. There's clearly one other thing you could do. And I should say, this is, before I show you the one other thing, this is the architecture for what I'm going to show you in what follows on 2D turbulence. So, I mean, it's basically the same as what I just showed you, except that it's applied to the Navier-Stokes equations. And one thing that we do, which I think is important, is that we're going to force the Navier-Stokes equations, and we would like this to be as generalizable as possible. I will come to this. And for that reason, we insert the force after computing the interpolants, with the notion being that it should generalize over forces. And then, at the end, right, there's pressure projection to project it onto divergence field. So this is the algorithm that I'm going to be talking about in a little bit. But another algorithm that you could use, you could call learn corrections, which basically means that what you do is you use the PDE, the discretization of the PDE as we've always known and loved it, to compute the update. And then you realize that, it was coarse, it was wrong, and you just add a correction based on the local environment. And this is called learn corrections. You might want this correction to obey certain properties. For example, in the Navier-Stokes equations, you might want it, if it's a correction to the velocity field, you might want it to be the divergence of something. So it was effectively, an effective stress. But this is another thing to do. And what I'm going to show you actually are a series of tasks in which we compete all of these against each other. Because I think an interesting question is, of the zoo of things you can try, what works best for some definition of best. And I say here, there's no a priori way of determining which of these methods is better, at least not to my knowledge. The only way is to systematically compete them against each other. And I guess this is like a clarion call for the need for mathematics. I mean, you would think that basically that one could prove things about these types of methods just to provide some guidance, because otherwise, this is purely empirical, which is what I'm about to show you. Okay, so let's talk about what we mean for a model to be better. So this is important. So we are interested in replacing solvers. The reason that solvers are based on the laws of physics, the reason we write down the Navier-Stokes equations is because we know that if we solve the Navier-Stokes equations accurately, then it is, if we were to make a measurement of the weather and it disagreed with our simulation of the Navier-Stokes equations, if we got the forcing right and everything, then there was a mistake in the measurement. Like, it's perfectly generalizable. And we don't want to lose that. So we seek both accuracy and generalizability, and both are important. What I'm about to say. So accuracy you can define in lots of different ways. So the current thing that I'm showing you right here is what is the task I showed you, which is we're trying to reproduce DNS on coarser meshes with bigger time steps. This you can play around with quite substantially if you want. And generalizability, we don't want, we want it to still be like the Navier-Stokes equations. So that's the game. And so in order to do this thing, which I think is kind of, in my reading of the literature, it's kind of lacking, that is tests of generalizability, we have a hierarchy of generalization tests. So one, which I'll call level one, is that you use the same forcing, but with different random initial conditions. So this is common in the literature. So I think this is a terrible generalization test for a problem like this. And the reason is because for any interesting problem, the solutions are chaotic and we roll them out for long times. And what that means is that after a couple of Lyapunov times, you've essentially trying a different initial condition anyway, because you've randomized relative to the one that you're at. And so the differentiation between train and test is very dicey with level one. So a better thing you can do is you can change the forcing function. And an even harder thing to do is to change the Reynolds number. So changing the Reynolds number is possible in a method where you have given terms have meaning. So, right, the thing about the terms, like the viscosity term in the equation, is we know what happens when we change the Reynolds number. We know that the smallest length scale has a scaling, that sort of is determined by the Laplacian. And so that's one of the advantages of using discretizations related to physics. So here's the way that we do this. We have Kolmogorov flow for our training, which is, this is at Reynolds number 1,000. We do tests where we have the same forcing for Kolmogorov flow, but we do it in a larger domain. We also do something where we just turn the forcing off and let it decay. And then we have a higher Reynolds number generalization test. So these are the tests. And now let me go through the results. So actually, maybe one more thing. So in order to do this, we have written a fully differentiable fluids solver in JAX. So I really like JAX because it is a automatic differentiation wrapper on NumPy. So it basically feels like scientific computing code. Like, I don't know about the rest of you, but TensorFlow and PyTorch are fine, but it doesn't feel like MATLAB to me, so it makes me upset. Whereas JAX basically is this way. And so we've written a solver in JAX. Because it's in JAX, it naturally, you can put in ML models however you want. And then you can simulate unrolled trajectories, compute losses, and do everything that you would want to do. It's automatically differentiable. This has now been open sourced as JAX-CFD. If you search Google JAX-CFD for computational fluid dynamics, you will find the solver and the data sets that we use for what I'm about to show you. This is an example of what the code looks like. This is just a simple flow, and it's functional programming. So equations dot semi-implicit Navier-Stokes, and then this unrolls a trajectory, and it runs very quickly. It runs quickly. You can run it it runs quickly, at least as long as it's small. And that's what we did to use. And this is what we built to do what I'm about to show you. So now technical specifications of what we did. So I'm going to show you simulations with Kolmogorov flow with Reynolds number 1,000. So the ground truth trajectories that we use for this have a resolution of 2048 squared. So we've chosen each time step in the ground truth solver. This is an explicit solver, and each time step obeys the CFL condition with factor 1/2. So what that means is that when we downsample the grid, which is what we're going to start doing, then we double the time step scale. So we always choose a time step which corresponds to the CFL condition with factor 1/2 on the grid of a given question and everything that I'm going to show you. So we downsample the solution to coarser grids. Then what we do is, so we have a set of downsample trajectories, we have the upscale trajectory, and then what we do is we demand that they agree. We basically train the models so that they agree. To do that, we use 32 different trajectories with different random seeds. We unroll them for 4,800 time steps. And as I said, we modify the time step to obey the CFL condition. The loss, what we found was that in order to train numerically stable methods, which is a major issue in this business, we need the loss to be a multi-step loss, which goes over 32 time steps. Actually, 32 is a number, it's a power of 2, but you would hope that you could do it. Initially, you'd think, oh, I'm just going to train on the next time step. And if you do that, then that actually destabilizes. And I think actually there are interesting mathematical questions here about just how to think about stability conceptually in these types of algorithms. So actually, amusingly, model evaluation was the most expensive part of this computationally. And the reason is because we were paranoid about generating stable solutions. And so for that reason, we generated much longer trajectories with tens of thousands of time steps to check that they were stable unrolls. Because if it destabilizes, I mean, if you do, because this is, we have to always be nervous about sticking machine learning into things. As soon as you do this, you've lost the theoretical guarantees that we all know and love. And, if you're going to empirically test, you have to empirically test. So, okay. So I'm going to now.
Sorry, this is a good point to ask the question in the chat. So Jetrin was asking, is the learned discretization update rule tied to the specific spatial discretization in the training data?
Yes, it is. Oh, wait, well, so it's tied to the, it is, so if you if you want to learn a rule on a 64 squared mesh, we learn at the moment different rules for every mesh size. So that's what we're doing right now. Now, I agree that, theoretically, there should be relationships between the discretizations at different resolutions, and you might even jointly train, but we don't do that at the moment. We just, we just train, we wanted to see if this worked, basically. And so, so we just trained at each mesh.
Okay,
other questions? Okay, so so this is an example of a comparison. So the top row of this figure shows the DNS at 2048 squared. As I said, this is Kolmogorov, and this is unrolling numbers of time steps. So this is DNS at 64 squared. So this is 64 squared. This is what that looks like. This is learned interpolate, and you'll notice these disagree. So you start to, like by this stage, they don't have anything to do with each other. This is our learned interpolation method on 64 squared. And you see that, so we've helpfully provided these yellow boxes so that you can see that the features are tracking. And so this is a low-level generalization test. This is just different initial conditions than the training set. And I already explained to you why I find this problematic, but it's an initial test. Now, one thing you can do with this, though, is to use it to see how much better you're doing. And so I want to introduce this plot. So I'm plotting vorticity correlation as a function of time. The blue line is 2048 squared. That's the ground truth. That's what we're using as ground truth. And then these solid lines are DNS, that is just standard algorithms at different resolutions. And what you see, of course, is, as expected, the lower resolution ones decorrelate with the vorticity. This is vorticity integrated over the whole domain more quickly than the higher resolution ones. This dashed line, the vertical sort of gray line, is 3 Lyapunov times. So this is the time at which you would expect it to decorrelate simply because of the chaos in the system. And this dashed line is learned interpolation at 64 squared. And so actually using this plot, you can compare how accurate this method is relative to the other methods, to other baselines. And what we find is that we're somewhere between 512 and 1024 with the 64 squared mesh. And so we're basically doing 10 times, we're learning we're maintaining the same accuracy with the 10 times finer grid. Now, 10 times finer grid, this is an explicit method in 2 dimensions. So you would expect that to be n cubed. So nominally, that should be a factor of 1,000 speed up. But of course, you have to pay. This is not free. You have to pay for the machine learning. And so I'm going to talk about that next. So actually, this is also, for a long time rollouts, you need to check the spectra, whether they agree. And this is a sort of convoluted way of plotting the spectra. But what it shows you is that at long times, the learned interpolation, which is this dot, agrees with the more accurate things. So, okay, computational efficiency. So it turns out that in this type of simulation, the utilization of the machine is actually relatively low typically because most of the time is taken reading numbers in and out of memory. And so for that mitigates the cost of the ML model. And so, right, so we actually maintain, so we on a TPU, the V4, the current version of the TPUs, we have about 10 times higher flops than the baseline solver. And what that means is that despite the fact that because of our interpolation, we have 150 times more operations, the solver is only about 12 times slower. So the gain is 10 cubed over 12, which is 80. So this is actually a real 80 times speed up in the time of the solver. And actually, to sort of illustrate this in the paper, we made this Pareto frontier plot where we plotted the runtime per time unit as a function of accuracy. And accuracy is measured by the time until the correlation is below some threshold. And these blue dots are the direct simulations of different resolutions. And these are the learned interpolations. And what you see is across resolutions, we push the Pareto frontier to the right, and that leads to about an 86-fold speed up, which is not enough to solve the problem I laid out in the beginning, but there's no sneezing at a factor of 100. A factor of 100 is a factor of 100. So that was just on the Kolmogorov test. So now what about the more general problems? So this is the same plot for decaying turbulence. So we use the same code. The code was trained on Kolmogorov, Reynolds number 1000. And this compares the DNS with the learned interpolation for the decaying turbulence. And you see, and these curves confirm that we're still at about a 10x, a 10x difference between the learned solver and the baseline. This is a more non-trivial test. This is a higher Reynolds number test. So in order to do this, so now we've changed the equation. So what we did is we know that in two-dimensional turbulence, the Kolmogorov scale scales like 1 over the square root of Reynolds number. So therefore, if we run at Reynolds number 4000, the Kolmogorov scale should be 1/2 of the size of the Kolmogorov scale at Reynolds number 1000. So what that means is if we take the model, and Jianfeng, this gets to the question that you asked, we take the model from the Reynolds number 1000 solver, and we simply pretend the mesh spacing was half of what it was, and then use it in the Reynolds number 4000 case. This, of course, relies on the asymptotic goodness of turbulent flows as Reynolds numbers gets high, and 1000 is not that high, but it's okay. Then this is what happens. And so this gives this is about an 8-fold enhancement, which I think is quite remarkable and clearly could be improved by studying the asymptoticness of this. But this shows that the solver sort of is learning the right things that even scale with Reynolds number. And then this is a similar thing on a larger domain, which also works. So, okay, so that is that. Now I want to just show you one other set of things, and then I will stop. I have 3 minutes left, if I understand right. So one of the things we did, and we did this at Google, and one of the great things about doing this at Google is we could just run as many jobs as we want. So I should say, the computational time that was in this plot is large, and I will explain. So what we did is we said, okay, so I just showed you this for a learned interpolation update rule, but of course, there are lots of update rules that you could use. You could use pure ML models, which I told you about, and you also could use learned corrections, which use physics, but in a different way. And for pure ML models, we use 2 different architectures, which are randomly taken from the literature. We used a form of a ResNet, and we also used an encoder process decoder, which has been put to good use in various applications. And what this plot shows, which I have bigger on the next slide, so this is the same plot. So what I've done here is I've taken each of the 4 examples that I've shown you. Forced turbulence, this is the one with different random seeds, larger domain, decaying, and more turbulent. And then these are different metrics. This is pointwise accuracy metric. This is statistical accuracy metric. And this is whether or not the algorithm blows up, which I haven't mentioned except to say that the algorithms that I've showed you thus far just don't blow up. And what this does is this competes the different types of architectures against each other. So this is learned interpolation, are the blue dots. The orange dots are learned corrections, and the green is EPD, and the red is residual network. So these ones are pure machine learning models, and the other ones are, these 2 are physics-based machine learning models. Each dot is a different random seed on the same training set. So each of these is a big training job, which is why there's a huge amount of compute in this plot. But what you see is very interesting, and I think is kind of what you would expect and hope, which is that actually pure machine learning models can do very well, basically. This is, especially the residual network turns out to be a disaster, but this EPD, if you look at pointwise accuracy and you compare it with the learned interpolation and the things that I showed you, for both pointwise and statistical accuracy, it does quite well. And it's a little more unstable, like some of them blow up, but you can find random seeds that don't blow up. So, that seems promising, but it performs much worse on generalization tests. That is, the larger domain, it does okay, which is kind of expected because it's a local model. So if you increase the size of the domain, it shouldn't matter. But when you change the forcing, at that point it breaks. And it breaks when you change the Reynolds number. And so this, I think, it sort of captures, I don't know if this is the answer to this question, but it's at least seems reasonable that the reason that you would want to use a physics-inspired algorithm is because you want it to generalize beyond the problem that you're solving. And if you don't have that constraint, then you can just do whatever you want, basically, and find a machine learning algorithm to help. So this is the thing. And I just as one last thing, and then I think I will wrap this up, is that you can of course do this on any PDE, not just the Navier-Stokes equations. And just for fun, we did this on an LES model. So we did this on the Smagorinsky model. The Smagorinsky model is the simplest type of an LES model. So that, of course, has an effective viscosity in it. And we just took the Smagorinsky model with Reynolds number 1,000, and we asked if we could play the same game. And we found that we could also, speed up essentially the solutions of the Smagorinsky model with this. And in fact, we did something amusing when we did this, which is that, so for those of you who have this in your head, what you do with the Smagorinsky is an eddy viscosity model. So you essentially modify the Laplacian operator. And what we did is we just, we didn't actually put the functional form in for Smagorinsky. We just demanded that the algorithm learned it. And it did, which it should have, because it has the freedom in its interpolants to learn it. So, okay, scaling and outlook. Okay, so we're early days in this business, but one can sort of, let's be mathematicians for a moment. I know this is supposed to be, sorry, this was not as mathematical as the other talks, but we can at least try to extrapolate. So the runtime, so as I said, this is only useful what I'm describing if it's fast. Otherwise, it's, as far as I'm concerned, a total waste of time. So the runtime obeys this scaling law. So we're using an explicit method in d dimensions, so it's n to the d plus 1. And there are a couple of factors that matter. So k is the effective coarse graining factor. So this is the number that we found to be about 10. So which is that we could decrease the number of mesh points by a factor of 10 and maintain accuracy. So then there's the cost of the physics model. There's this prefactor, which is the standard numerical algorithm prefactor. But then there's overhead from machine learning, which is what one has. So right now in our hands, running on TPUs, this ratio is 12. The ratio of these two factors. Now, we have not tried to optimize this at all. And I think that, the example of Razor shows that you can speed this up. There's no doubt that this can be sped up. But anyway, this is a factor of 12. If one pushes this to 3 dimensions instead of 2 dimensions, then, so we have 80-fold speed up at the moment, but with 3 dimensions, you get, of course, another factor of n over k, which should be another factor of 10, which would give 800. Which would give a factor of about 800 in speed up. And this doesn't solve the intractable scaling problem I mentioned at the beginning, but every factor of 1,000 helps. And we are hard at work. We've made some progress, I should say, towards making this work in higher dimensions, which that's what I will say. So that's my talk. I appreciate your attention. I want to just end by reminding you the people who did this, and in particular, Stefan, Dima, and Jamie, who built this JAX CFD code base and really made the last demonstration work, which was non-trivial. So at least I think. So thanks.
Thanks, great talk. Are there any questions from the audience?
Yeah, Michael, can I ask a very quick question? First, congratulations for impressive results. It's pretty inspiring. So I was wondering if you are confident that some of these hybrid models and the fact that they seem to be showing this very nice sweet spot between accuracy and stability, if one can kind of open the box and try to extract some knowledge that can be then generalized even further, like what is the actual network figuring out that we haven't figured out?
I think this is a really great question. So we have not worked on this very much, and I really would like to work on this more. One thing that we did early, which I can go back slides, in the original paper on 1D, we were really worried about this. And I became obsessed at some point with, it's just Berger's equation, for crying out loud, right? So just to extract the scaling laws of shocks and Berger's equations from these weights. And actually we failed at this miserably, basically trying to do this. That's not to say that you would fail, it's just that we failed. But one thing we did manage to show is that the model learned upwinding, which was Well, I mean, which is stupid. That doesn't answer your question either, but that's, so it's not totally ridiculous. And this we've sort of continuously show, actually, if you look in the appendix of our PNAS paper, the one that on turbulence, you will see information about the stencils that show upwinding type things. So I think the more interesting version of the question that you just asked, though, is can we figure out what basis that the model is computing in? Because at the end of the day, we've set this up, I think, so that we're just learning better interpolants, right? What we're effectively doing, I think, at least the theory is that we are, instead of needing to use whatever, 5, 10 points per Kolmogorov scale, we're lowering that number by a factor of 10. And we're presumably doing that by, learning the local basis. And one would really like to know the basis. And then maybe if one learned what the bases were, then I think you're right. Maybe you could just forget this, throw this in the garbage can and just start computing with this basis, which would be a better way to do this. And we just haven't done this yet, but I think it's a really interesting direction.
Thanks for the answer.
Grant? See your hand is up.
Okay, so I just was wondering if you could comment a bit on the transferability as you change, say, the parameters of a fixed PDE. So these learned, interpolants, do you need to completely relearn them, or do they serve as a good initial condition for further optimization?
So we have explored this very little, so I can't really say anything. The only thing that we've done that's definitive on this that was sort of enough for me to say was this Reynolds number experiment, where we increased the Reynolds number to a factor, by a factor of 4 and demanded this experiment, right? Which I actually think this is a pretty stringent test to demand this. And so, but this isn't exactly what you just said. Now you could ask, so to reformulate what you just said slightly, Grant, like you could imagine taking the model at Reynolds number 1,000, doing this scaling and then fine tuning on it at Reynolds number 4,000. I think there's no doubt that would do better and it would converge more quickly. I mean, ultimately what we want to do is to produce asymptotic models, like that's and that's going to require some sort of thing like what you're saying, like asymptotic and Reynolds number, and whatever other PDE you want with its dimensional parameters. I mean, I think it's one of the things we've been struggling with, actually, maybe another way of commenting on this in case is what is the right, suppose this turns out to be useful. I mean, at the moment this is still exploratory, I think, but suppose it turns out to be useful, like what's the right form of it? Like, for example, one doesn't want to retrain for every parameter setting in every equation. On the other hand, there aren't that many equations that we're interested in. So it's not so bad, especially if you get a speed up. I mean, it might well be worth it. So I don't know. We haven't done a lot. I think there's a lot of interesting things there. It's related in many ways to Joan's question too, about the bases, and how that changes. Sorry, that wasn't a very good answer, but that was everything we know.
I mean, I think that's, I agree with everything you said. I mean, I think it's an interesting question to explore, because I think that's one of the, principal utilities of an approach like this, if you can transfer it between, different regimes of behavior of the model.
Yeah.
Jitrin?
Can you hear me?
Yes.
Yeah, Michael, very interesting talk. So can you comment how the learned discretization can be applied to unstructured meshes or the different geometries? For example, in real applications, the boundary may not be regular.
Yeah, that's a good question. That's something that we've been working on. I mean, in principle, these are local operators, right? I mean, in principle, we're learning an operator. So there's nothing in what I've said that makes me think that it should be constrained to the types of regular meshes that we're using. I mean, that's the only thing that I can really say that's concrete right now. Does that make sense? But I think it's a good question. I mean, or maybe do you disagree?
Yes, in principle, discretization is a discretization of operators. But if I understand correctly, your current formula is tied to the regular grades as well, right? So how can transfer the learned rule to unstructured meshes, for example?
Yeah, so I agree with you that unstructured meshes require different ideas, will require additional ideas. So maybe that's the way I would say it. But I really, I think it's very interesting, and we just haven't done very much with it.
Okay, thank you.
Thanks.
Other questions from the audience? Okay, if there are no further questions, let's thank Michael again. And now we're going to have a short round table